So today we're going to go over the Lecture 10 pre-lecture. This is when we're going to start chapter number 15. Just as a note, we will start Lecture 10 with the end of chapter 14. So if you haven't watched the pre-lecture video, pre-lecture 9, that will be helpful in this lecture as well. But when we get into chapter 15, we're going to start talking about chemical equilibrium. So with chemical equilibrium, to understand equilibrium, we've kind of talked about it in several different chapters, but we're going to look at basically what's called a reversible process. So if we have a reversible reaction, one reversible reaction we looked at was the dissociation of a weak acid. Back in 1211. So with a weak acid, something like HF, HF is considered a weak acid. As we add it into water, it breaks down into hydrogen ions and fluorine ions. However, we also have those hydrogen ions and those fluorine ions coming together to produce HF. So this would be considered a reversible process. Together, we get the equilibrium process, HF, going to H plus F minus, and these are going to be in the aqueous state for all of them. Right, so we've got a reversible process where we have a forward reaction and we have a reverse reaction. With chemical equilibrium, we have a reversible reaction, and in this reversible reaction, the forward reaction rate is equal to the reverse reaction rate. So we would say the rate of the forward reaction is equal to the rate of the reverse reaction. And then we could also say, in addition to this, that both reactions are still occurring. So we still have the forward reaction occurring, we still have the reverse reaction occurring. They're just occurring at the same rate. We call this a dynamic equilibrium. Because everything's still occurring as it was before. Now, because we have these things occurring at the same rate, our concentrations are going to stay consistent. So our rates are the same, our concentrations are staying the same. That doesn't mean that our reactant and product concentrations are the same, just our reactant concentration isn't changing, our product concentration isn't changing. It has reached an equilibrium amount. So let's consider the Haber process. Haber process is a specific reaction where we have nitrogen gas reacting with hydrogen gas to produce ammonia gas. I would say that the rate of that, we're going to call that Kf. and then two ammonia molecules react to produce N2 gas and H2 gas. So this would be our reverse reaction. So if these are in a closed container, so that none of our gas goes away, we have the equilibrium process. N2 gas plus 3H2 gas is in equilibrium with 2NH3 gas. Okay, and it's arbitrary. You can choose whichever one's your forward, whichever one's your reverse, as long as you have the equilibrium arrow in between. So at equilibrium, we would say that the rate of our forward reaction is equal to the rate of our reverse reaction. Where the rate of our forward reaction is equal to Kf N2 H2 3, as this is we consider this kind of like an elementary step, so the stoichiometry is taken into account in this rate. And then the rate of our reverse is Kr and H3 2. So we would say that since the rate of our forward reaction and the rate of our reverse reaction are equal, Kf and Kr expressions are equal. So Kf N2 H2 cubed equals Kr and H3 squared. And we can come up with an expression where we have our Kf's on one, or our rate constants on one side, our concentrations on the other side. So I'd say Kf divided by Kr is equal to NH3 squared over N2 H2 cubed, where this is a constant, and this relates our concentrations within this reaction, or within this equilibrium. So even though these concentrations aren't the same, they will always equal the same constant at the same temperature. So let's think about what's going on graphically. So we can think about this in terms of concentration versus time, or rate versus time. So we've got at time 0, we start out with an amount of H2, an amount of N2. Our H2 will go down, our N2 will go down. And we're going to start out with, so this is our H2, this is our N2. Then we're going to start out with no NH3. But over time, we're going to increase in that concentration. Okay, and when these kind of level out, when these concentrations level out, say that right about here, they all level out, that is the point at which we reach equilibrium. And our concentrations no longer change. With our rate, we're going to have a beginning rate for our forward reaction and a beginning rate for our reverse reaction. The rate of our forward reaction will start out high, go low. The rate of our reverse reaction will start low, go high. But again, they are going to come to an equilibrium point, like so. Just make that look a little better. So when those rates are equal, we have reached equilibrium. So you can look at equilibrium at either your reactants and product concentrations aren't changing, or your rates aren't changing. Okay, so we talked about up here this constant. We can look at that constant. It's called the rate, the equilibrium constant. So we want to look at the equilibrium constant and the equilibrium constant expression. So our equilibrium constant, we call this Kc, big K, little subscripts, big K, little subscript c. So our rate, that's little k. Our equilibrium constant, that's big K. So let's take the general equation. AA plus BB is in equilibrium with CC plus DD. If we want to write the equilibrium constant expression, we would say that Kc, big K again, is equal to concentration of C to the C, concentration of D to the D, concentration of B to the B, concentration of A to the A. Okay, so on top we have our products. On the bottom we have our reactants. That gives us our equilibrium expression. And if we know our concentrations, we can solve for our equilibrium constant. As a note, the concentrations are in molarity. And this Kc, this equilibrium constant, if it's a C, it's talking about concentration. Now, note, unlike our rate law, this does not depend on our reaction mechanism. It only depends on the stoichiometry. So, equilibrium constant doesn't depend on the mechanism, only the stoichiometry. So it is different from our kinetics, where it depended on the mechanism. So keep that in mind. Okay, our equilibrium constant can also be expressed in terms of pressure. So our equilibrium constant expression in terms of pressure. So we call this, our equilibrium constant is Kp, if we were talking about in terms of pressure. So this works for gases. And it works for gases because of our ideal gas law. Remember, PV equals nRT. So pressure is equal to N over V times by the constants R, or the constant R, and the temperature. So as long as we have our temperature the same, we can relate pressure and molarity, right? So, to write our equilibrium constant expression in terms of pressure, we would say that Kp is equal to the partial pressure of C to the C, the partial pressure of D to the D, partial pressure of A to the A, partial pressure of B to the B. Okay? So we have partial pressure of A, for instance, is the pressure of the atmosphere times by our mole fraction of A. Our mole fraction of A, hopefully you guys already know this already, but just in case, moles of A divided by total moles. Okay? So we can use partial pressures in this equation to determine our equilibrium constant in terms of Kp, and then we can relate Kp and Kc using the following equation. So Kp is equal to Kc times by RT delta N. So we have our two equilibrium constants. So our equilibrium constant in terms of pressure equilibrium constant in terms of concentration. Our R value is 0.08206 liters atmospheres over moles Kelvin. Our temperature is in Kelvin. And then our delta N is going to be our product moles minus our reactant moles. So you're just going to add up your stoichiometric coefficients. So let's look a little bit more at this. Our delta N, in the case of AA plus BB, going to CC plus DD. You would say N is equal to C plus D minus A plus B. Okay? So you're just going to add those stoichiometric coefficients in a balanced equation. Okay, so that's everything. Keep in mind that we're also going over the rest of Chapter 14, so if you haven't already watched Lecture 9 pre-lecture video, watch that, and then I will see you guys on Tuesday.